What's up? I'm Vin, and today I want to go through the 2021 AP Calculus BC free response question number 6. So let's get started. For part A, first thing we have to do is state the conditions necessary to use the integral test, and then determine the convergence of this series here. So in order to use the integral test for this series, we need to look at the corresponding function 1 over e to the x and say that it is continuous, positive, and decreasing from 0 to infinity. So now that the conditions are met, we could actually apply the integral test. So we're going to look at the corresponding improper integral. Since the series is going from n equals 0 to infinity, our limits of integration are going to be 0 and infinity. And the corresponding function for 1 over e to the n is 1 over e to the x. So here's our improper integral. And to evaluate this, we're going to take the limit as b goes to infinity, and we're going to swap out that limit of integration infinity with the letter b. And now we could rewrite the integrand as e to the minus x dx. And for the AP test, you should really show up having certain formulas like this. So if I take the antiderivative of e to a constant times x, it really helps to know that this is 1 over k e to the kx plus c. So that way for a question like this, you don't have to do a u substitution. You could just jump right into this. So here I could say this is the limit as b goes to infinity. And since this is a definite integral, I don't have to write my plus c, but in this case k is equal to -1. So if I have 1 divided by -1, that's just going to be minus e to the minus x, and our limits are 0 and b. So now to evaluate this here, and I'll just put this part here in parentheses, this is going to be the limit as b goes to infinity, and I'll write this as -1, so I'll just write the constant on the outside, and then I've got e to the minus b minus e to the 0. So we'll close this parenthesis and we'll close the bracket. And now to simplify this, this is the limit as b goes to infinity of, we have -1 times e to the minus b is 1 over e to the positive b minus e to the 0 is 1. So to simplify this limit, this is just going to be -1 times 1 over e to the b as b goes to infinity is going to 0. So I have 0 minus 1. And now to simplify this here, this limit is just going to simplify to -1 times -1, which is +1. So we now have enough information to answer this question. What we should notice here is that the improper integral converges. So if the improper integral converges, that tells us here by the integral test that the corresponding series is going to converge as well. For part B, what we're trying to show here is we're going to use the limit comparison test to show that g of 1 converges absolutely. So if we want to show that g of 1 converges absolutely, we should take the absolute value of g of 1, and that's going to be the series from n equals 0 to infinity. We have the absolute value of -1 to the n over 2e to the n plus 3. And if we simplify this, this is the series from n equals 0 to infinity of 1 over 2e to the n plus 3. So we're trying to show that this series here converges, and if you could show the absolute value of a series converges, that means the series converges absolutely. And remember, absolute convergence also implies regular convergence. So now we're going to apply the limit comparison test. So we have the limit as n goes to infinity, and we're going to look at the ratio of the general term of both of the series. So we're looking at the general term here. We have 1 over 2e to the n plus 3 over this series here, 1 over e to the n. So we're taking the general term of both of them. And now here, what we have is the limit as n goes to infinity. And if we do the algebra, we just use keep, change, flip, or you could just multiply the top by the reciprocal of the bottom. This is going to give us e to the n over 2e to the n plus 3. And now when we work this limit out, you can see there's an invisible 1 in front. Since in the numerator and denominator, the leading terms are e to the n, and they go to infinity at the same rate. To find this limit, we just look at the ratio of their coefficients, and that's just going to be 1/2. And we should comment here that 1/2 is positive and finite. So the way the limit comparison test works is that if we could show that this limit is positive and finite, then either both series converge or both series diverge. But since from part A we said that this series converges, that tells us that this series here, the absolute value of g of 1 converges as well. So from here, we'll just write out our conclusion. We could say that the series G of 1 converges absolutely. For part C, we want to determine the radius of convergence of the Maclaurin series for G. So for this one, we're going to use the ratio test. And that means we're going to take the limit as n goes to infinity, and we're targeting G of x here. So we're going to look at the n plus 1 term. So we're taking the absolute value of the n plus 1 term, which is negative 1 to the n plus 1. We'll just make this neater, times, and let's just separate this. So we have times x to the n plus 1 over, we have 2e to the n plus 1 plus 3. So we're doing the ratio of the n plus 1 term divided by the nth term. So just know, if I were to divide by negative 1 to the n, x to the n over 2e to the n plus 3, that's just going to flip to this expression here. So I'd have times, and I would have 2e to the n plus 3 over negative 1 to the n, x to the n. So it helps to just be able to do that little bit of algebra right away, so you don't have to write out too much. And now here we could just do a little bit of algebra and simplify stuff. So notice here that I have x to the n plus 1 over x to the n. So x to the n is going to cancel out completely, and it's going to simplify the top expression here to just x to the first power. And on bottom, what I have is I have negative 1 to the n, and I have a negative 1 to the n plus 1 here. So this is going to cancel out, and this is going to turn into just negative 1 to the first. So if we simplify this, this is the limit as n goes to infinity of, we have the absolute value of, and notice what I have left. I have negative 1 times x, and I'm going to write the fraction part separate. So I have negative 1 times x, but then I also have 2e to the n plus 3 over 2e to the n plus 1 plus 3. So the reason why I'm separating this stuff is that this is the limit as n goes to infinity. And 2e to the n plus 3, 2e to the n plus 1 plus 3 is always positive. But x could be positive or negative, so that means this is going to stay behind in the absolute value. And notice the absolute value of negative 1 is just positive 1. So that allows me to rewrite this limit as the limit as n goes to infinity. The only thing that has to stay behind in the absolute value is x. So I have the absolute value of x. Absolute value of negative 1 is positive 1. And the absolute value of this fraction, once again, is just going to be, I have the absolute value of something positive, so I could just get it out of the absolute value. So we get here. The only thing I want to do a little different is, instead of writing 2e to the n plus 1, I'm going to write 2e to the first times e to the n plus 3 like this. So I'm only breaking off one of the e terms. That way you could see that when we take the limit as n goes to infinity, if you focus on this part, notice I have an e to the n and an e to the n. So as n goes to infinity, I have matching leading terms, so the limit is just going to be the ratio of their coefficients. So the only thing that's going to make it out of this limit now is I have absolute value of x, and then the ratio of e to the n on top is 2 over the ratio of e to the n on bottom is 2e like this. And just know, for the ratio test, the only way that this is going to converge, the only way this series is going to converge, is that when we apply the ratio test, this is going to be, this has to be less than 1. Okay, so then we just set all of this stuff here in our limit to be less than 1. And now this simplifies a little bit. 2 over 2 cancels, so I have the absolute value of x over e has to be less than 1, which tells us that the absolute value of x has to be less than e. And once I get to this step, I can come up with my conclusion here. Our radius of convergence is just equal to e. Remember, they're not asking us for the interval of convergence, so don't fall in the trap of setting up the inequality and testing the endpoints for convergence. We only have to identify the radius. So at this step here, we could say the radius is equal to e. For part D, we have the first two terms of the series for g of 1 are used to approximate g of 1, and we need to use the alternating series error bound to determine an upper bound on the error of approximation. So for something like this, my thought process is to use the upper bound, or the alternating series upper bound. We have to look at, if I'm approximating g of 1 and I'm only using a partial sum with two terms, then my error is going to be less than or equal to the first unused term, which would be the third term. But another trap that they sprinkle into this question is, notice the series starts at n equals 0. And if you were to plug in n equals 0, that would give you negative 1 to the 0 over 2e to the 0 plus 3. So notice here that you have something that's non-zero. So that means that the series, the first term is going to start at n equals 0. So the first unused term, if it's the third term, is actually going to correspond to n equals 2. So that means, to answer this question here, that the absolute value of my error is going to be less than or equal to the first unused term, which is the third term, but that's going to correspond in this case to n equals 2 since I'm starting at n equals 0. And if we were to plug in n equals 2, that's going to give us -1 squared over, I have 2e to the second plus 3. So the absolute value of our error is going to be less than or equal to just 1 over 2e squared plus 3. So this is going to be our solution to part D. Okay, well, this is going to conclude this video on the 2021 AP Calc free response question number 6. If this video was helpful, please like and subscribe. It really helps me grow the channel. And if you got any requests, just leave the topics you want me to cover in the comment section below. And thanks for watching.